Welcome to a screencast on the properties of liquids. The objectives of this screencast are to distinguish between adhesive and cohesive forces, to define viscosity, surface tension, and capillary action, and to describe the roles of intermolecular attractive forces in each of these properties or phenomena. Let's start by considering the intermolecular forces experienced by a liquid, and as a specific example, let's look at drops of water on a spider web. Within a water droplet, there are attractive forces between water molecules, and these forces hold the molecules close together and makes the water bead up to form droplets. These are known as cohesive forces, which are intermolecular forces between identical molecules, between one water molecule and another. Now at the interface between a strand of spider web and a water droplet, attractive forces between the water molecules and the surface of the strand make the water cling to the spider web. These are called adhesive forces, which are intermolecular forces between different molecules, in this case between water molecules and the spider web molecules. All liquids have cohesive forces between their molecules and adhesive forces between their molecules and those of another substance, and the characteristics of these attractions determine the properties and behavior of a given liquid. For example, gasoline versus antifreeze versus motor oil, or alcohol versus olive oil versus honey. The first property of a liquid we'll consider is its viscosity, which is a measure of the liquid's resistance to flow. Some substances, such as gasoline, flow relatively easily. Liquids like this, we say, have a low viscosity, and this is due to weaker intermolecular forces and/or smaller molecules. If the attractions between molecules are not very strong, or if the molecules are relatively small, they can flow past each other relatively easily. Now, other substances, such as motor oil, do not flow as easily and are said to have a high viscosity. And high viscosity liquids have stronger intermolecular forces and often are larger molecules, and these factors hinder the ability for molecules to move past each other, which results in a slower flowing liquid. Viscosities of different liquids can actually be measured, and they are measured in units of pressure times time. This table gives the viscosities of several common substances, and they're measured here in millipascal seconds. As an example, octane, which is a component of gasoline, consists of molecules that have 8 carbon-long chains. These are nonpolar molecules. They're not that big, so they have relatively small intermolecular attractions, and octane has a fairly low viscosity. Now, motor oil, on the other hand, consists of chains of carbon atoms that are 20 to 40 or so carbon atoms long, and even though they are also nonpolar, because they're much larger molecules, they have stronger attractive forces and therefore a much higher viscosity. Note also that motor oil has a pretty broad range of viscosity values. This depends on the specific types and sizes of molecules used, and these are chosen to meet the specific required operating conditions for whatever engine or circumstance the motor oil is needed for. Another characteristic of a liquid is its surface tension, and technically this is the energy needed to increase the surface area of the liquid, or the force needed to increase the length of the liquid surface. But let's look at this on a more molecular level, and here is a water droplet, and we're looking at molecules at the surface and molecules at the interior of this droplet, and notice that at the surface we have unbalanced cohesive forces between molecules, and that causes the surface of the liquid to behave somewhat like a stretched rubber membrane. So interior, this molecule is attracted in all directions. That's balanced forces. At the surface, this molecule is attracted on the sides and below, but not above. And so those are unbalanced forces that causes this stretched rubber membrane surface effects, surface tension effect. And when we have substances like water that have relatively strong intermolecular forces and therefore a high surface tension, we get some interesting effects. For example, insects can walk on water because of these unbalanced forces at the surface. Water makes very spherical droplets, especially when they're very small. And in fact, it can do both at once. Here's kind of an interesting effect, an insect, a spider walking on the surface of water with a little water droplet there. And we also get some interesting thin layer effects, such as shown here with this swimmer, all due to strong attractions between molecules, creating this strong surface tension. Water has a very high surface tension. We can measure surface tension. It's measured in units of force per length. And here are surface tensions of some common substances given in millinewtons per meter. And water's already been mentioned. It has a pretty high surface tension. But mercury has an even higher surface tension. And water and mercury readily coalesce or bead up, whereas things with lower surface tension like ethanol and octane don't bead up or form droplets as easily. Now, liquids can also undergo something known as capillary action, and this occurs when a liquid flows within a porous material due to the attraction of liquid molecules to both the surface of the material and to other liquid molecules. And the example here is wine wicking up a paper towel. And this occurs because of the strong attractions of water and ethanol molecules in the wine to the OH groups in the towel's cellulose fibers, and also the strong attractions of the water molecules that are being attracted to the cellulose to other water and ethanol molecules. So this is why wine wicks up this paper towel. This is how cotton towels soak up water when you dry off after a shower. And numerous examples of capillary action can be discussed. So capillary action occurs in cells called xylem in plants. This is the reason why plants, or part of the reason why plants are able to bring water and dissolve nutrients from the soil up through the roots and into the plant itself. It has to do with attractive forces between water and the interior of the xylem cells, and then, of course, cohesive forces between water molecules and other water molecules. And you can see this in action pretty visibly in a real simple way. Take a piece of celery, submerge the end in a glass of water that has some food coloring in it, and in a little while you will see the color actually be transported up into the celery leaves. Another example is if we need to collect a small amount of blood, for example, to test the amount of glucose in the blood of somebody who has diabetes. You can prick the finger of the person and put the end of a small glass capillary tube into the drop of blood, and adhesive forces between the molecules in the blood, in those in the glass surface, draw the blood up the tube, and this continues until the weight of the liquid in the tube exerts a downward force equal to the upward force due to capillary action. One more example, capillary action is also the basis for something called thin layer chromatography. It's a laboratory technique commonly used to separate components in a mixture. This is based upon different rates at which these components are drawn up an adsorbent surface by the capillary action of a particular solvent. And here we have maybe colored components of an ink being drawn up and separated with different rates of movement up a piece of chromatography paper. And that is it for Properties of Liquids screencast.